In this video clip, we're going to look at this graph problem. The solutions for solving this problem does not use any graph theories or graph traversals. In short, let's look at what this is. So starting with the following graph. So a graph is a abstract data type that could be used to represent complex nonlinear relationship between objects. So what you see here is a collection of nodes. So this graph consists of nodes and a whole bunch of edges, and these edges do not have any direction. So this is also what we call undirected, and also we don't see any cycles in them, meaning these nodes do not, form a cyclic relationship. So this is also what we call undirected acyclic graph consisting of these nodes. These are parent-child nodes, as you can see here. Starting with, for example, very top one, 1. So 1 is what we call root, but in other words, this is what we call parent. And each node could also have a descendant, in this case, 3. The direct descendant is what we call child, right? So in this case, both 1 and 3 form a parent-child pair, right? So let's just take maybe 5 and 7 here as an example here. So 5 and 7 is illustrated right here. So 5 is parent, 7 is the child, right? So 5 and 7 forms a child. And the reason why there's a relationship here is just because of the edge, right? The edges is the line between, right, the two nodes. Okay, let's look at maybe another one. So 15 is the parent, 9 is the child. So now we also see that this is represented here. So what you have here is basically an array of these nodes, right? An array of these pairs represented as this. We're interested in finding a list of orphan nodes. So orphan nodes means there are no parents. So for all intents and purposes, you can look at them as roots, right? Well, these are root nodes, 1, 2, 4, 5, right? They don't have any parents, so these are orphans, what we call orphans. So I'll find a list of them. The second part of the problem is to find a list of single parent nodes, right? So let's look at what those are. So this means that we're looking for nodes with only one parent, right? So 3 is one of them. Yes or no? No, right? Because 3 has actually 2 parents, 1 and 2. But what about 5? Well, 5 has only one parent, right? Which is 4. So 5 is good, right? We can also have maybe 8. Right? As you can see, there's only one parent, which is 4. How about 9? 9 is not, right? 9 having 2 parents, so 9 is not good. So we got 5, 7. What about 7? Actually, 5 and 8. 7, yes, right? As well as 11, right? So in this particular graph, we got 4 single parent nodes. Okay, so that's what the problem is. You gotta get a list of orphan nodes as well as a list of single parents. So let's just look at how we approach this problem. The intuition is just by looking at this problem, for each pair of parent and child. What we can do is enclose the examinations. We can come up with several dictionaries. These are count dictionaries, or the number of occurrences for each of these nodes, right, with respect to each other. Let's look at number 3, right? Number 3 is a child, right? It's a child to 1 and 2, but parents to 6. But let's just look at treating, 3 here as a child. So we can do a dictionary count and count the number of parents, by each child, right? So parent count by child. So we can see that 3, has 2 parents, right? 1 and 2. And for example, 9, right? If treating 9 as a child, then we'll know child 9, right, has 2 parents, 4 and 15. So if we look at 9 as a child here, well, we can see that 9 has 15 as well as 4, right? Since 9 is treated as a child. So that's one form of dictionary. And the other form is basically the other way around. Let me just clear this. Well, we have the number of child per parent, right? So if we treat, let's say, number 3 as a parent, and we can, basically see that, from this graph, there's only one child to 3. So looking at this in reverse, we can see treating 3 as a parent, finding all of the parents associated with 3, we see that there is only 1 occurrence of a child associated with 3, so on and so forth. For example, 4, if we treat 4 as a parent in this case, then we'll see that 4 only has 3 children, right? 5, 8, and 9, as we can see here. So that's the second count or count dictionary, right? Parent count by child. So with that intuition, let's move on with our code. This is our bootstrap code. We have our main and the solutions method, find orphan single parents pairs, right? So the purpose is to find a list of 0 parents node, what we call orphans, and a list of single parent nodes from a undirected acyclic graph represented by this input right here, which is an array of array. So that said, let's begin coding. We're talking about having a return values being a list of a list, right? Array of lists. This is what we're gonna do. Array list, integer, and this is the integer type, right? So what we've got in there. This is the return value, which is our array list with 2 lists in there, right? So let's just make sure that we got that down. Okay, so that said, let's move on. In this case, we can probably just return it right here and make sure that everything compiles, right? All right, we need to create 2 HashMap. Technically, we should use hash sets, but just make it simple here. This is our, there are 2 of them. These are integer. And the first one is called child count by parents, right? The number of children that we've got, right, per parent, per node. And this is new HashMap. Okay. And the second one is, let me just make a copy of it. The second one is the parent count by child, right? So this is the number of parents each child, right, has in the node. So we want to iterate through this entire pair to establish these 2 counts. So once we get these 2 counts, then we can study the relationships between the 2 to arrive at the information we need. So to iterate through these, right, we can do this integer I less than pairs, right, dot length, right? So remember, this is 2-dimensional array, right? So we're simply looking at the number of pairs that we've gotten there, and because we want to iterate through all of them, right? Child count by parents. Here's the thing. So child count by parents is a HashMap, it's a key value pair. So we want our key to be the parent, right? Which is, let's just do puts here. And the parent is represented by, remember, this is a 2-dimensional array, right? So for each of these pair, the parent is actually the 0 index, right? 1 index is the child, 0 index is the parent. So that's it. So we're using parent by the number of values that we got. So what is the value? Value is the number of child, right? So just do this. How do we get the number of values? So first of all, based on the key, so we have to basically get, right, the number of children that we've got already inside the HashMap. So to do that, we can do child count by parents, right, and then get, right, pairs 0. This is I, this is 0, right? This should give us the number of them, right? And then we, right, if there is already a value inside of this child counts by parents, then we get it, right? And then we plus 1 to it because we just found 1. But sometimes they might be 0. So we in this case, in case there's no key value pair in this, we can do what's called get or default. This is going to give us the number of pairs that we've gotten there. We can add 1 to it. If not, by default, we can just have it as a 0, right? So in this case, we do 1. So this entire thing guarantees that we can get the number that we need for this value. So in other words, we can also just copy and paste this without having to have a an extra integers in there, right? So we can just make sure that this works. Let's set up the second HashMap. So the second HashMap is parent count by child, right? So for each child, how many parents do we get, right? So this is, let's just make sure that we have that here. Parent count by child. In this case, we're going to do the same thing. But in this case, we're going to index this by the parent, which is at index 1, right? And then we want to say parent count by child, right? Get or default pairs 1, 1, or defaulting to a 0 if there is none in there. But we want to, once we find it, we want to add 1. So this gives us the number of parents each node, right, for each node, and the number of child, right, per parent. So we've got basically two count dictionaries here. And so the next logic is to, now that we've got this established, the next logic is to look into each child count by parents and parent count by child to see if we can establish the list that we need. So the first thing is, let's do the child count by parents, basically the number of orphans that we've got here, right? So the logic is this: if this is already, if this is empty, that means there is none. So we wanted to make sure that list is empty. So what we can do is to ensure that our return value, remember the very first index is the one that we need for a list of orphans. So we can simply just set up a brand new list now that's completely empty, right? So to do that, let's just create this as is. And so this gives us that. But what if there are nodes in this child count by parent? So in this case, what we want to do is to create an entire list. This list is going to contain everything that we need in there, right? New array list, integer, right? Okay, so what we need here is to iterate through our child count by parents. And the way to do that is we can use the Java iterator. Just get the iterator out, it equal child count by parent entry set iterator, right? And while, right, it has next. So let's just move on, iterating through it. So the very first thing we want to do is to pull up the, using the iterator, and pull up each pair, right, which is a list of, right, parents and child. So to do that, we use map entry, and this is a key value pair. So this is a key value pair, and basically that is integer, right, integer, right, this pair. And this pair has got map entry. And we can pull up the iterator and says this is the next one. So what we want to do is this parent node cannot be a child node elsewhere. So we wanted to make sure, right, while you pull this up, that this one does not exist in the parent count by child too. So let's do that check. If this is someone else's parent, then no, right? This cannot be the orphan. This cannot be root, in other words. So to do that, let's double check, right? So this double check involves looking into this pair as a key, right? Get key, and see if this key exists, right, in that dictionary. If this does not exist in that dictionary, then we can safely say that, hey, this is our root. Therefore, we want to add it to that, right, list that we got there. So this is a pair get key, right? And this should give us a list of all of the orphans that we've got here. So notice that this is that entire iteration that we need to get our orphans, but we also need to, right, make sure that we've got our list of single parents. So a list of single parent nodes should be in return val 0, right? So same logic here. Let's just quickly write them. So parent counts by child, right? If this is empty, then what we can do is to make sure that our return val 1, right? This is our second list, is our array list. But that array list is completely empty, right? This entire thing is completely empty. Okay, so this takes care of the edge case there, right? But in this case, let's make sure we have the else situated as well. So this is the same thing here. Let's just copy this. I don't want to retype this whole thing. This is the entire, this is the new list that we need to do. And then same thing, we're gonna iterate, iterator, right? Iterate this thing. And this is parent count by child. entry set dot iterator. Now this is just the iterate pattern. So once you do this a lot of times, it becomes second nature. So this is has next, right? And let's just iterate through every single pair inside of this. And again, we're going to use map entry, right? So this entry is a template. So this is the integer, right? And this is the pair that we're talking about here. So this is map entry. IT next, okay? All right, so this gives us the pair. So let's just double check to see. Now listen, for every single pair, if for every single key that comes out of this pair, and that key is the child key, which is the get value, not the key itself. If the number of counts is greater than 1, that means there's multiple parents, and then we don't want that. Since we're talking about single parents, so if this is a single parent, then basically each, right, get value. Remember, this is a key value pair, right? So the value, right, has to be 1. If this is 1, it means there's only one parent, right? Then we want to add it to this, right? This pair and this list, right? So we want to add that key, which is our child, right, with single parent from this. So this should give us a list of what we need. So what we need to do is this is actually if right here, right? Okay, is we want to persist this as in return val dimension 1 here. This is our list. So now we've got 2 lists here, and here obviously doing the same thing in dimension 0. Right? So this list and that list is totally different, right? These are 2 different lists here. One is this is for the orphan list, and this is for the single parent list. And now we've got them all persisted in here and returning this. Okay, let's double check the syntax and make sure everything is correct. And then we can correct these as we go. Okay, so right. So just make sure on the very top that you have Java util array list or extras, so you can get the whole thing persisted here. So let's double check again. All right, so the iterator spelled wrong. This is line 39. Okay. All right, so this works. Let's just write some code. This is our test code. And basically what we need to do is to create a solution class. And then we can actually just system out print line this whole thing to double check, right? So what's going to be printed is this entire 2-dimensional array. And this is the method that we want. And the input itself is parent child pairs. Okay, so this is probably not going to give us much because this is an integer, right? So what we can do is we can persist this entire thing, the list, and then just print them out there, which is very easy. So let's just do this. Since the return is actually an array of lists, we can just say this is that, and then solution find, right? And this is the parent child pairs that we want. And so that's the result right there. We are interested in list 0 and also list 1, right? So let's just double check. There we go. Okay, so this is the correct solutions. The very first list is a list of orphans or list of roots, right? These nodes do not have any parents associated with them. The second list is a list of nodes with single parent, with one parent in it. So this is the correct solutions. Let's look at time and space. So there is a for loop here going through every single pair. So this is the O event. There's also not a while loop that goes through every single pair individually once you have these maps set up. So this is 2 times the event, and if you just keep going here, there's another one too. So 3 times O event. So by and large, this is the O event for time. In terms of the space, the storage itself is O event because you're never going to have more than n number of pairs, right? So this is n in terms of number of pairs. So that's the time and space for this problem.